Well, hello, Brunky Tech here, where we believe technology is for everybody. Today we're going to talk about fusing your PCB and if it's required. We'll go over various different technologies like this PTC Resettable Fuse and this glass fuse to make a determination if these are viable options for your PCB. We'll do an analysis to determine if one is actually required. Now, I know that'll get on some of the hardliners' wrong side, but sometimes you might not need a fuse on your PCB. We'll go through different analysis to help you make that determination. All right, we're going to walk through an example I have right here on a controller that I designed back a few years ago. So I simplified this a lot just to show the main parts of the controller. We have an input fuse that limited the current of the entire controller. We had a filtering circuit, and then we had a 3.3 volt regulator that regulated the supply voltage to the microcontroller. From the microcontroller, we had outputs that control these high side drivers. We have 4 high side drivers which ran various loads off the vehicle. So I must ask you, how many current limiting devices are on this controller? Now let's talk about the different types of fuses we can use on our PCB. First off, we have these glass fuses. So these are really old. They work actually pretty well. These are rated as 250 volts. You can have a various different sizes of these. When you're rating your fusing on your PCB, I guarantee you won't have an issue finding a proper size fuse for your PCB on these. The downside is on your failure modes and your PCB, I guarantee this connection will be the first thing that goes. There's historical data going back since implementation of these, indicating that this is such. Second issue is these guys like to break. Well, they're supposed to break, but then when they do, you got to take that out of your PCB and put it back in. This might or might not be a problem depending on your implementation. If you have a cell phone, ain't no way you're getting in there. There's also some sort of current draw that are from these that you have to take into account. There's power losses. Then you have these PTC's Resettable Fuse. They come in this package, a 3-hole package. They also have a package that lies on the surface board. So these do a good job of what they need to do. Unlike the glass fuse, when these break, you don't have to replace it. It just has to cool down. Once it reaches the proper temperature, it'll fuse again. So the disadvantage of these, of course, there's power losses with these as well. Also, it's a little bit harder to find a proper size fuse. I was looking at a 28 volt board that I was doing and designing, and I was looking for a fuse that was about 20 amps. You know what? I couldn't find one. So we had to do something else. And then there's the last one I want to discuss here, and that is an IC chip that has a fuse inside of it. So these guys are fast acting. They're pretty small. They're probably the most expensive one out of them all, but they work how they're supposed to, and they have an automatic trigger on and off, on and off. There's some power losses. So regardless of your implementation, there's going to be some power losses when you go into a fuse. Now there's other implementations that you can do, but I won't go into there, but use your imagination. I'm pretty sure there's plenty of things you can come up with. All right, let's go back to the question I asked you earlier. How many current limiting devices are in this microcontroller? So we have a fuse, which protects you from overcurrent and short to ground conditions. We have this 3.3 volt regulator, which protects you from the same. And all of these 4 high side drivers actually have current regulation built into these. Also, you have the microcontroller, which talks and communicates with these high side driver. These high side drivers happen to give the microcontroller the current readout. The microcontroller can actually limit the current on these devices as its needs fit. Looking through this setup, how many layers of protection does this controller have? When you're considering fusing your PCB, you need to look at 5 different considerations. So you have your safety and regulatory considerations. Safety, your actual customer, you got to think of it from their end. Your entire system and the intent use of that system. and protection of the hardware. There's plenty of standards and regulations you can design your PCB to. And this is all depending on if you want to actually market this product, where you want to sell it. I mean, you can get away with selling stuff on Amazon without going through it. Typical box stores, they'll at least want a UL certification for your device. And so you got to take all that into account. So you got to follow by the applicable standard regulations if you need to. And just following by those standards would actually give you a better product. So these standards have been built over the years to meet certain safety protocol, and they're there to help you. You know, even if you don't have to meet it, you can read through the standards and gives you some idea of what needs to be done. So never deviate from these standards if your applicable product falls within these standards. So one thing about these standards is they're not set in stone per se. You can actually request to change these if you run into a better way of doing that doesn't comply with the standard. So they update these as time goes by when new points are added to them, so it makes them better over time. To view some of these standards, you can go see the UL listings. If you sign up to their website, you can actually view the applicable standard. You can't get a copy. Those are probably $1,000 a piece, a little too much. But just looking at those might give you ideas of safety considerations you could put into your device, even if it's just something that you want to do for your home. And there's also ISO standards as well. All those need to be purchased. And that's kind of my rant. Getting all these safety standards for you to build a product can be a pain in the butt. And because there's hundreds of them. And then they all reference each other. So you'll get one standard and it'll go through there and it'll reference the second standard. And you're like, oh, you got to go to this second standard in order to complete the whole entire circle. Pain in the butt. I wish they just post them online. UL at least has them posted. You can't get a hard copy though. Then now you go to a safety. So your product shouldn't exhibit any safety risk. And of course, this is geared to your particular product. So if you have a motor right here, obviously, you intend this motor to be attached to some driver somewhere, so you're not anticipating any safety regulations behind this, with the exception of the motor blowing up. Obviously, the motor can't blow up, but you're intending that this device gets consumed by somebody that knows how to use it. That's how it's sold. And then you have USB devices. Obviously, if you plug in a USB device into your USB hub, you anticipate that it's going to work. Even if you pass a standard and your product is unsafe, you need to fix that safety issue before you release product. And you should always design with the intent that it's going to fail in a safe state. That's also additional consideration that you need to take. And finally, the higher the voltage, the higher the danger. I have this little car. It's got two 1.5 volt batteries, so 3 volts. So the safety for this is basically probably a reverse diode. Now the controllers for the motors actually probably have a current limiting on them, but that's probably not by intention. It just so happens that even the cheapest chip for motor controls have current limiting on them. All right, let's take a look at this microcontroller. How many layer protections do we have? First, we have the fuse that is inside the controller. That is one layer of the protection. Fed from the fuse is the 3.3 voltage regulator, as well as the 4 high side drivers. So that's the second layer of protection. But there was something I didn't mention about. That was the system implementation of this controller. When we take a look, there's an additional fuse that is added on to the input of the controller. So you have a 12 volt, 20 amp fuse going into the controller. You have a 12 volt, 20 amp fuse inside of the controller. Now, after looking at this system diagram, does the system view change your mind on the protective scheme on the microcontroller? Now, other considerations you have to take into account is your end customer and what they expect. So depending on what you make, depends on what their expectations are. So I have this motor controller that I made that provides an output for a controller of the motor. So what are their expectations on this? Whatever I have listed on the data sheet. So I say it's got current regulation and it's not going to mess up your microcontroller as long as you hook it up correctly. And that's its hit. That's the target customer. So then they know somewhat how to use this. That's how that goes. You have this camera. It's got a USB. Obviously, when you plug it into the USB, you expect it not to break. So you just have to keep the consideration on who's using the device and how they're expected to use it for in the end. Second thing you have to take account is the system implementation. So this is another device I built. So I planned on using this and plugging it into my power supply. This has 2 voltage regulators on it. And I'm expecting to use the current limiting on this device to kick in if something goes bad on this. So that is a system implementation that I planned on using. Now, if I put this on a battery, would that change what I do? Maybe. I might put a fuse in there because there's only one protective device on there. So you got to take account of your system protection, of what the plan uses on there. Finally, protection of the hardware. Probably the last thing. If I have a 3.3 volt regulator on this device and it goes straight to the microcontroller, if it blows, what's my plan on this hardware? Is it still good? No. No. So there's certain protections that you can put in for the hardware. Sometimes it matters, sometimes it doesn't. Almost done. My hair is starting to look like the ancient alien guy. All right. I got a good example here in what we call a design FMEA, or failure mode effect analysis. People cringe when they hear this. Extremely rare, probably won't ever happen. But I would look it down because it has design implementations that we can add onto the controller to make it better. So we have this 3.3 voltage regulator. And what if it's shorted to 12 volt power? So that 12 volt power bypassed the regulator and went on that 3.3 volt line. What happened? So that voltage goes through the microcontroller on an GPIO, and it goes out and turns on a high side driver. So now your high side driver is stuck on. Your circuit's not going to trip because it's not an overcurrent event. Probability of this actually happening is extremely rare, but the severity is extremely high. Why? Because we cannot have inadvertent movement in our system. It's a safety standard in there that we had, and it never can happen. The second end result of this is a broken microcontroller. So we give this a rank of 9. Second, we can have a 12 volt short on that line to ground. What'll probably happen is a breaker would trip. Is that a 0 probability of that? There's a small probability. What's the severity? It's a 2 or a 1. And then you'll end up with a broken microcontroller. You'll probably have to throw out the whole entire thing and get a new one. Another one you have is the 3.3 voltage regulator breaks and unopen. So there's no power going to the microcontroller. Probability is 2 or 1, very, very low. Severity is 2 or 1. So you have a broken 3.3 voltage regulator. We rank this as 1. So when we take a look at the design, what did this analysis tell us we needed to do? We needed to add some additional protection onto the controller. We added a fuse onto the 3.3 voltage regulator right as soon as it goes into the microcontroller. That fixes that severity condition and brings it down to a 1. So what happens if you have voltage on that line go down to the microcontroller? The fuse trips. So let's go back to that system view that we had. So now that we've taken into account what our entire system looks like, what would I do differently on this implementation? So I would take out the 12 volt fuse on in the microcontroller. Thank you for joining in, and I hope you enjoyed this session. If you like my content, hit a thumbs up, subscribe, and I got a Twitter, Brunky Tech. If you if you're on Twitter, if you want to follow me, go ahead and go there. I'm always posting different projects that I haven't posted videos on, so you might get a little sneak peek. All right, thank you. Have a nice day.